All right, so this is where we left off last week. Last week, if you look at the last piece of notes, we were discussing the reactivity of metals. And I have it to the right of the screen here. You all remember this from last week, where I told you all potassium was the most reactive metal. And as you go downwards, it gets less and less reactive. And even though we were doing metals, I also mentioned the halogens. Fluorine is the most reactive halogen. And as you go down, it gets less and less what? Reactive. Well, we don't have AT on the syllabus. We only go up to iodine or iodine when it comes to the CSEC syllabus. Now, how it works, right? Whenever you have a more reactive metal, it can displace a less reactive metal. For example, right? The best way to teach this is through examples. Look at question 1 here. In case you didn't know, Ag is silver. So Ag is silver. Let's say you decide to mix silver and potassium nitrate. So for the time being, potassium is combined with nitrate. So silver comes up. And you're looking at the metals here. The two metals that are in battle are silver and potassium. Who is more reactive, potassium or silver? Who is more reactive? You just have to look at the chart here, and it's going to be to the side for all the questions. Right, Naomi, correct. Who is more reactive, silver or potassium? Stephanie, correct. Right, and all you're doing is looking at the chart, and the higher it is, the more reactive it is. So sodium comes up, but he is trying to displace the sodium, potassium, sorry. But silver cannot do that because potassium is more reactive, meaning that he's more powerful. So you know what's going to happen here? Nothing. The silver is just going to be by himself, and potassium nitrate will just remain as what? Potassium nitrate. Because something that is less reactive cannot displace somebody who is more reactive. Let's look at the second example. For those who didn't catch on in the first one. In the second example, zinc. So you mix pure zinc, because zinc is by himself here, with silver nitrate. Now tell me something. Is silver more reactive? Sorry, is zinc more reactive than silver? Well, what do you all think? Is zinc more reactive than silver? And the answer is yes. Look at it. Zinc is quite up here and silver is quite down here. So you know what's going to happen? Silver is going to tap on Mr. Silver's shoulder and tell him, hey, get out, and throw him out. So the silver is going to end up by himself, and the zinc is going to be combined with who? The nitrate. It making sense so far? Right? Because zinc was more reactive than silver, he was able to displace him. That's the actual technical term. It's able to displace the silver. Let's look at number 3. Number 3 is not really about metals. It's really about the halogens. And the halogens that are in question are chlorine, who is by himself. And right now, the iodine is combined with the potassium. So we're looking at the halogen chart. Now, if you look at it, chlorine is clearly higher than iodine. So chlorine is more reactive than who? Iodine. So what's going to happen? The chlorine is going to say, hey, I'm more reactive than you, iodine. Get out. So it kicks out the iodine, right? And the chlorine takes its place. Now, obviously, we have to balance this equation, right? For the time being, I'm not balancing it, but I just want to make sure everybody understands the concept there. We're not balancing it right now. I know if you attempt to balance it, Iodine is diatomic, so it has to be 2 here. Chlorine, remember, we had 2 chlorines to begin with, and potassium, but the charge on potassium is +1. The charge on chlorine is -1, so you have to put a 2 here. And if you have 2 of this, well, then you must put 2. Oh, I end up balancing it, right? Does number 3 make sense? That chlorine was more reactive than iodine. So based on the reactivity series, it was able to displace or kick out the iodine. Do you all think you all can do 4, 5, 6, and 7 for me? I'm really not concerned about balancing the equation. I just want you all to use the charts to figure out if the item can be displaced. And if it cannot be displaced, well, then there's no reaction. Like number 1, you got the same exact thing. There was no reaction because silver in number 1 was unable to displace the potassium. Right? So try number 4, 5, 6, and 7. And let's see what you guys come up with. Right? Remember, I'm not judging you on the balancing of the equation. I'm not judging you on that right now. So number 4, right? So for number 4, you have copper. Where's copper? It's copper versus iron. Unfortunately, copper, right, is lower than iron. So copper cannot replace iron. So nothing is going to happen. So you just write back the same exact what? Equation. Number 5. Iron and lead. Those are the 2 competitors, iron and lead. But for number 5, iron is higher than lead. Look at it. Iron is higher than lead. So iron can displace lead if it wishes. So the lead gets pushed out and the iron what? Takes its place. So this one actually has a reaction, number 5. Number 6. I don't think copper can replace aluminum, right? Because copper is one of the lowest. You see, copper, silver, and gold, those are like the 3 lowest, right? So nothing is going to happen here. Now, I'm just letting you know, right? Anytime nothing happens, you have 2 options. You can write back the same exact expression, or you can just write no reaction. Any one will give you what? The same amount of marks in the exam. Okay? Most people choose to write back the same exact thing, and they might put in brackets no reaction as a safeguard. Number 7. Can aluminum replace lead? Where's aluminum? Aluminum is quite, yes, I think that can happen. Aluminum is quite up here and lead is quite down here. So aluminum is more reactive. Yeah, he's going to kick lead out and aluminum is going to take its place. How much people got all correct? Right? Easy stuff, right? So all right, so for those who follow any little storyline where we're on a different planet, some group of scientists, landed on the planet. This was something I did a long time ago, so it isn't the best storyline, but apparently there's a little alien monster living on the planet, right? And he's hungry, and of course, he's going to attack the humans who landed on the planet at some point in time. All right. I won't get too invested in story. Like I said, it's a very old storyline, right? So the alien tells them they have 30 days to give them all his food, or he will eat them instead, right? Whatever. All right. So here's what we're going to do now. It's a kind of realistic situation, in fact, right? You ever thought about how humans first got metals out of the ground? I don't know if y'all ever thought about it. Y'all ever heard about these ages in life? The Bronze Age, when it had the Stone Age first, after the Stone Age, well, which age came after the Stone Age? The Stone Age is the age where people were using stones to make weapons. What came after the Stone Age? Was it the Bronze Age or was it the Iron Age? I don't know if it was the Bronze Age, correct. So bronze is a type of metal, but studying bronze is really not on the CXC syllabus. And after like the humans learned to make weapons out of bronze, which is obviously stronger than stone, they discovered how to extract iron out of the ground. And iron, well, is really, really strong, and it's easy to craft into weapons. So then began the Iron Age. But the thing about it, when you go into the ground and you try to extract iron, you don't get pure iron. Instead, you get many other things. You might get iron oxide, which is rust. Also, let's just say on the very, very rare possibility that there was pure iron in the ground. That iron, first of all, is going to be mixed up in the rock, right? It's going to be encased in rock, and it's going to have sand, dirt, mud, and just washing it is not going to be enough, right? But most of the times, well, when you dig iron out of the earth, it looks like this. You all have seen a picture in front of you all here. This kind of orange brown rock here, you call that iron ore or hematite, right? That is how iron looks when you dig it out of the ground. Does that look like nice, pure iron that you find in the hardware? Well, when you go to buy a strip of iron, is it that color? Or is it nice and silvery or grayish in color? You all know the answer to that. It's nice and grayish or silvery in color. So the question is, how do they go into this rock and extract the pure iron from it? Also, what about aluminum? Aluminum is another type of metal found in the earth. But when you go digging for aluminum in the ground, you don't find pure aluminum. Instead, you get something called aluminum ore. And what its official name is bauxite. And it looks like this, pretty scary looking. So there are two metals on the CXC syllabus that we have to discuss in detail. How they extract iron from the ground and how they extract pure aluminum from the ground. Just do me a favor, right? Oh, something was blocking the screen here. This here is a general chart of how you extract certain metals from the ground. In case you didn't realize, this is the metal reactivity series. From potassium to aluminum, we use electrolysis. Zinc, iron, tin, and lead, we use burning with carbon, right? So to extract iron, which is the one on the syllabus, we have to what? Extract it by heating it with carbon. Aluminum, we have to use electrolysis. Copper and mercury, all you have to do is take the rocks you find in the ground and just burn it in the air. Nothing special. And what will happen, that is enough to separate the copper or the mercury from the rocks. Silver and gold, no extraction needed. Silver and gold are so unreactive that after billions of years in the Earth's crust, they remain as silver and gold. The silver and gold don't react with something, with anything. So when you find them in the ground, even after like 4 billion years, it's still pure silver and gold. Take down everything on the screen there, right? You have to memorize everything on that screen there, right? Let me know when you guys are finished. And we'll be discussing iron first for yourself. Right? Let's see what's going on here. Right. So they're going to extract some iron, right? So let's see what's going on here. To extract iron, the first thing you actually need is a kind of chimney, a kind of furnace, right? So let's see how this will look here. Oh, sorry about this. Wait. So some guys, something happening. All right, great. So this is the diagram here. So what you're seeing in front of you is a kind of tall chimney. It is be real high, like meters high. Like if you're driving on the highway, you will see this chimney from a distance. Also, it's filled, sorry guys, I just having a little speech problem here, sorry. Let's take my time before I mumble too much. All right, so what we're gonna do, this furnace, we're gonna heat it up. At the bottom of the furnace, it's about 1800 degrees Celsius. And as you go upwards, when it gets slightly cooler, all the way to 200 degrees Celsius. At the top of the furnace, you're going to throw in three things. You just dump it inside there. Iron ore, remember the iron ore is the hematite. The iron ore is what you dig out of the ground. You're going to put something called coke. Coke is not the same thing as cocaine. Coke is actually carbons. It's a material that is rich in carbon. And you also put something called limestone, which is basically calcium carbonate. So you dump all three in, and also you have to make sure this whole thing is supplied with air. You have to make real sure. The reason for the hot air is that hot air contains oxygen, and you need a lot of oxygen for this process to take place. So here's the first thing that's going to happen. At the bottom of the furnace, right, it's going to be real hot. Remember, it's 1800 degrees Celsius. What's going to happen at that temperature? The carbon, which comes from the coke, is going to mix with the oxygen that's coming from the hot air. When those two mix, you're going to get carbon dioxide. Nothing amazing yet, right? You just mix, and it's only two things can happen. Is either you get carbon dioxide or you get carbon monoxide. This one gives you carbon dioxide. Once the carbon dioxide is created, this carbon dioxide that we just created is going to mix with more carbon from the coke. So the carbon dioxide you just created mixes with more carbon, and you get what? Look at this properly. This is carbon monoxide because it only has one O. Carbon dioxide has two O's. Now here's what's going to happen. The carbon monoxide that you just created, look it over here, right, is going to mix with the hematite, with the iron ore. And you all know which one is higher in the metal reactivity series. If you look back in the chart, you all see carbon here, and you all see what? Iron. Who is more reactive, carbon or iron? Look back in your metal reactivity series from last week. Who is more reactive, the carbon in the carbon monoxide or iron? Salamatu correct, Naomi correct. The carbon is more reactive, right? I'm just going to put a little arrow here so you remember, right? The carbon is more reactive than iron. So what's going to happen? The carbon is going to kick out the iron. So you notice the iron, if you look at the after reaction, the iron gets kicked out on its own, and the carbon steals the oxygen. So that is how the process works, okay? Also, you will notice by the iron, it have the letter L. Why is it the letter L and not the letter S? Isn't iron a solid? Why did the examiner, oh sorry, the person who is me, put the letter L there and not the letter S? Right, Salamatu, correct. Because it's molten, right? Stanisha, correct. Remember, this whole thing's so hot inside here. The solid iron that was created is actually in liquid form because it's melted. And guess what's going to happen? The iron is very dense. This liquid iron is very dense. So the liquid iron will sink down to the bottom of the furnace. And when it sinks down to the bottom here, it have a little tap here and it flows out. Real simple, right? Because iron, liquid iron is dense. So it just sinks down to the bottom and it have a little tap here. You just open it and the metal, the liquid metal just flows out and you collect it and you sell it and make billions of dollars, right? It's theorized that this process was, it was discovered by accident close to the Iron Age, right? They suspected that people threw iron ore into fires by mistake, and then they put what? Burnt wood on it by mistake. Now, burnt wood contains a lot of carbon. So they think it's an accidental process that led to the discovery of how iron was extracted from into its pure form. But here's the other thing now. Iron ore is not just Fe2O3, right? Iron has a lot of water in it. When you dig that out of the ground, it have plenty of dirt, mud, sand. It has so much gross things around it. And no matter how good you wash that, you can't wash out all the sand. You can't wash out all the mud. So how do they get rid of all of that? Well, you all notice we haven't used the limestone as yet. How much of you all realize the limestone, the calcium carbonate, has not been used in the process as yet? We use the coke, which has the carbon in it, right? We had the iron ore, but the calcium carbonate has not been used. So let me show you the use of that now. So look over here. The calcium carbonate, whenever you expose calcium carbonate to a very hot environment, there's something called thermal decomposition. Don't let that scary term get to you. You know what that really means? Certain things, when you apply heat to it, the heat causes that thing to break down into different products. Simple explanation for something called thermal decomposition. And it just so happens when calcium carbonate is exposed to heat, it's broken up into two things: calcium oxide and carbon dioxide. What happens next is that the calcium oxide is what you care about. The calcium oxide is going to mix with the silicon dioxide. You're probably wondering, what is silicon dioxide? Silicon dioxide is sand. That's a fancy term, but that's the chemical formula for sand. And when the calcium oxide mixes with the silicon oxide, which is the sand, you get calcium silicate, which is this guy here. Now, it just so happens, calcium silicate, when you make it, it's in liquid form, and that also sinks down to the bottom, but it's not as dense as the iron. So the calcium silicate will float on the iron. So it's always a little bit higher than the molten iron. And you have a separate tap for that. Now, calcium silicate is actually something pretty useful, right? You call it molten slag, right? And you're going to get some uses of it. So even though the sand turned out to be a nuisance, well, when you do this process, you get rid of the sand, plus you get something useful, calcium silicate. And once again, because the calcium silicate is not as dense as iron, it floats on top of the molten iron, making it very, very easy to tap off or to separate from the molten iron, right? In this process, if you all notice that you get kind of dangerous gases, right? Well, when you do this process, you get carbon dioxide and you also get what? Carbon monoxide. So those are the waste gases here. If they ask you that in the exam, like what harmful or waste gases are produced in the extraction of iron? And now you know the answer for that 1 mark question. Carbon dioxide and carbon monoxide. Take down everything on this screen. And guys, I really advise you, whenever you get time, draw and write back all of these equations over and over and over until it just sticks in your head. Let me know when you're finished. I'll give you 5 minutes. So just for recording purposes, right? If they were to ask you, what happened to the Fe2O3, specifically that question, they will ask if the Fe2O3 was reduced or oxidized, right? I'm giving you the answer because it's such a popular question. The answer, it was reduced, right? You notice the iron lost its oxygen. Usually when something loses its oxygen, you notice it went from Fe2O3 to pure Fe. That means it was reduced. Like if you do the calculations for it, like you calculate the charges and everything on it, you would realize that the Fe2O3 would have been reduced. Okay, so I'm just giving you the answer for that particular question. All right, so let's go. All right, let's see what's going on here. All right, so now that the team has been able to extract the iron out of the ground, they're going to start making weapons to fight the monster. All right, but here's the thing. When you extract pure iron out of the ground, like you see the process we just did, even though it's better than stone and maybe better than bronze, it's probably not the best iron in the world. And there is a reason for it, right? You see the iron that we just got, that we opened the tap and it flowed out, you usually call that cast iron. Cast iron, no matter how much you try to clean that iron or to purify it, when it comes out of that furnace, about 4% just be impurities mixed up in that iron. And of course, that makes it a little bit weaker. So cast iron, the iron that just came out the furnace, this usually be the cheapest type of iron. You just call it cast iron. I'm sure you hear your parents talk about it at some point in time, right? Well, when they was building a house and whatnot. What you just need to do to get rid of the impurities, you just take that cast iron and blast it with a whole set of air rich in oxygen, like it's special air that has extra oxygen in it. And when you do that, you just oxidize the impurities. And then it is changed into a stronger type of iron called wrought iron, right? Obviously, wrought iron is more expensive than cast iron. And to make it even stronger, you take the wrought iron and you add carbon and some other substances, but the main thing is carbon. And when you add carbon mainly to wrought iron, you just get steel. And steel is way stronger than the other two. And steel is super expensive, right? So take down this little flow chart. You need to memorize it as well. Right, now here's the thing. Remember this thing called slag? Slag was the calcium silicate. Take down this here. Calcium silicate can actually be used to make fertilizer, or it could help to build roads. So you say calcium silicate, you shouldn't throw it away. Anybody who has an iron factory or a steel factory, they just sell the calcium silicate, or even right there on the compound, convert it to fertilizer or materials to build roads to get some extra money. So it's not just about selling the iron. You can sell the calcium silicate as well, right? So just some advice in case you all want to grow up to build a factory, become one of those big businessmen or businesswomen who sell iron. You can become very, very rich if you own a successful iron company, by the way, right? That's how you become a billionaire, right? All right, so I'm not too sure what this is about. All right. Oh, so what Riggs here? Sorry, Jimmy. Jimmy is the guy in green here. What he did, he took some of the iron or steel and he made aeroplanes. And now the captain is angry with him. Anybody can tell me why the captain is angry at him, right? Why is the captain angry? Right, set, correct. Anybody else want to tell me why the captain? No, yeah. All right, some of you all are getting it. When you're making aeroplanes, you cannot use iron. They don't use iron to make, but any type of iron, whether it's wrought iron, cast iron, or steel, they don't use that to make aeroplanes. Iron or any of its products is too heavy. You have to use aluminum, which is significantly lighter than what? Iron to make aeroplanes, right? So iron or steel planes simply will not fly. But even if it does fly, it's going to use too much gas to get it up into the air. It's not going to be efficient enough, right? It's the weight is the problem, right? Right. So Riggs is just explaining to them, well, the same thing I just said, that you need aluminum in order to make the airplanes. All right, so we're going to learn now how to extract aluminum from the ground. Right. So once again, if you look back at this chart, the chart that you already had from before, to extract iron, I showed you that you have to burn it with something containing carbon. However, aluminum is in a different category. Aluminum is above carbon. So you cannot use carbon to extract aluminum. Instead, you have to use electrolysis. Now, lucky for us, we did electrolysis about 3 weeks ago. So this is going to be super easy for you guys. Right? Right. But it's a few extra things that you need to know. Here's what we need. We actually need 2 things. You need to get the bauxite. Well, the bauxite is the raw aluminum oxide that you dig out of the ground, right? And you need something called cryolite. Now, cryolite seems like something from the future, some kind of alien substance. But yeah, this here is the chemical formula for cryolite. Na3 aluminum, what is Al aluminum F6. Cryolite does actually make the extraction of aluminum a little bit easier, not a little bit easier, plenty easier. Don't get me wrong, you can extract aluminum from bauxite without cryolite. It's just the cryolite will make it easier to do. And the examiner will test you on that. He will ask you, hey, what's the procedure? He will say, well, the bauxite is purified. That means they wash it down and clean it as much as possible, right? And then the purified bauxite is dissolved in molten cryolite at 900 degrees Celsius. Take down everything on the screen. Now, of course, you're probably wondering, but why does the cryolite make the entire process easier? I'll have a note on that for you in a little while. All right, so let's see what the next slide holds for us. Right, so here's the thing. the bauxite is dissolved in molten cryolite at 900 degrees Celsius, right? Now, without the cryolite, right, the melting point of the bauxite would be 2050 degrees Celsius. That's a huge difference, right? So if you wanted to melt the bauxite by itself, because in electrolysis, you need it to be a liquid. You'll remember when we were doing electrolysis, the first thing we did was molten sodium chloride. Well, instead of molten sodium chloride, we are doing molten aluminum oxide. But to melt aluminum oxide by itself, it's 2000 and something degrees Celsius. You're going to require a lot of energy to do that, and it's going to be very, very expensive. So when you mix it with cryolite, the melting point is reduced to only 900 degrees Celsius. That's less than half. Also, molten aluminum oxide is a poor conductor. When you mix it with cryolite, it becomes a better conductor. And for electrolysis to happen, you need the liquid to be as best of a conductor it can be. Because the better of a conductor it is, the smoother the electrolysis process will go. So you take down everything in green now. And the examiner loves to ask you this question, like, what is the point of adding the cryolite? And you have the two reasons in front of you. All right, so let's go. Oh, somebody wants more time. All right, no. All right, so we have a little diagram here. Now, I know this looks fancy, right? But at the end of the day, when you're doing electrolysis, remember you just have a battery, right? The side connected to the positive side of the battery is the anode, and the side connected to the negative side of the battery is the cathode, right? So this side is the positive and this side is the negative. Now look at this diagram here. It doesn't look like the normal electrolysis diagram. But if you take a closer look, right? This part here, right? It's just a different shape, right? It's a big container, and the lining of the container is connected to the positive side of the electricity. So this here is the cathode. And this part here, that's connected, sorry, the cathode is connected to the negative side of the electricity, and the anode is connected to the positive side. So in other words, we get a different color here. This is the shape of the anode. I know it's weird looking, but this is how it looks in real life, right? This here is your anode, and this lining over here, this black lining is your cathode. It looks very odd, but that is how it looks in the industry, right? Great. So what's going to happen at the end of the day? These are the two reactions you have to remember. The aluminum, remember, it's molten aluminum oxide. So when you take Al2O3 and you melt it, the aluminum will get separated from the oxygen. Aluminum has a charge of 3+ in this case, and the oxygen will have a charge of 2-. All the charged aluminum will move towards the cathode, and the Al3+ will gain 3 electrons and change to neutral aluminum. That's this reaction. Then the oxygen goes towards the anode, where it loses 4 electrons. Remember, I transpose the electrons here. When you throw across the positive 4 electrons on the other side, you'll get negative 4 electrons. But remember, I told you all, you're not allowed to say that you lose 3 electrons. So you have to transpose it to the other side. Remember, an oxygen is what? Diatomic. So the charged oxygen will lose 4 electrons, and change to neutral oxygen. This here is the equation at the anode. Right? I know this is going to be kind of hard to draw, but still take a shot at it, no? And try your best to draw it here. Right? And this gold part here, but the gold part is the molten aluminum oxide with the cryolite. Right? So the cryolite is mixed inside here with the aluminum, but the cryolite doesn't actually take part in the reaction. It doesn't get discharged at the anode or the cathode. The cryolite is just there for two main purposes: to lower the melting point and to make everything a better overall conductor. Right, so I think I should give you 5 minutes for this one because you have to draw that diagram. All right, now here's the next thing we could do. You see, once you extract the aluminum, right? The aluminum basically comes out pure enough, right? You can make an alloy of aluminum called dura-alumin. Now, dura-alumin is 95% aluminum mixed with 4% of copper. So you put some copper into the aluminum and you put a little bit of magnesium and manganese. And when you do that, you get something called dura-alumin, sorry. Now, the truth is, they don't really use pure aluminum to make aeroplanes. They use the dura-alumin to make the aeroplanes because dura-alumin is way stronger than aluminum. So take down everything in green, right? And in the exam, if they ask you what are the benefits of dura-alumin, and it's pronounced kind of tight, I'm sorry. It has it's very low in density, which is good. It's stronger than aluminum, and it's more resistant to corrosion. All right, let's go. All right, so the day has come, 30 days is up, and of course the worm here is ready. Well, has come to collect the food, but the humans are going to fight, it looks like. And they attack the worm. Oh, we don't need to do this here. We went through that already. All right, so basically we finished the whole of metals there, and that's basically the whole of metals. So I had put together some stuff. This is from last year, but like I said, from last year. Some quick revision questions. Without looking back, do you all think you can put those particular metals in the correct order without looking back? Take a try, right? So it's just going to be revision now because we finished with metals. Right? Try your best, try your best. Metal plus oxygen, what will we get? I gave you that answer in your notes. A metal plus oxygen will get you what? I'm going to give you a chance to explore all of these questions and send the answer. First one. Metal plus oxygen is a metal oxide, right? You'll see that straight out in your notes there. A metal plus water is a metal hydroxide plus hydrogen gas. Everyone seeing this one? Right? Metal hydroxide plus the hydrogen gas. Well, I should write it up. Hydrogen gas. Right. And a metal plus acid will give you a salt and hydrogen gas. Right. These are actual past paper questions. I just copy and I don't have the years, right? I just, but you know, I just copy and paste it. What is formed when magnesium burns in air? Remember, when they phrase the question like this, what does the air contain? It contains oxygen. So magnesium is a metal and you're combining it with oxygen. That's the same thing as air. A metal plus oxygen will give you a metal oxide. So you will get magnesium oxide. That is what they wanted. And a lot of people send that answer, right? How should metals more reactive than carbon be extracted? If something is more reactive than carbon, that is, it's above carbon in the reactivity series, which method do we use? Electrolysis, or do we burn it with carbon? You copied down that table about half an hour ago. Right, Bridget, correct, Alia. Now, Salamatu, check it back. If something is above carbon, it is used electrolysis. Aluminum is above carbon, so you use electrolysis for the process. Right? So take down all of those questions with all the answers, right? We're only going to be doing questions on today and next week. Next week, we have a whole set of past paper questions prepared on metals. All right. The next question is a true or false question. When a metal reacts, it behaves as a reducing agent because it ionizes by losing electrons. These electrons are given to the other reactant, so the other reactant can gain electrons. Is that true or false? The simplest one here is sodium and what? Chloride. I guess that's the easiest example. All right. Some people saying it's true. A handful of people are saying it's false. All right. So what happens with sodium and chloride? Sodium will give an electron to who? Chlorine. Remember that, right? Sodium will give an electron to chlorine. So sodium loses electrons. Remember oil rig, right? So the L is for loss, right? So because sodium loses an electron, it's oxidized. But remember, when something is oxidized, the type of agent it is will be the opposite. So if sodium is oxidized, then he is a what? Reducing agent. So this is what? True, because they're saying that it behaves as a reducing agent. Remember, I explained that last week. If something is reduced, then it would be an oxidizing agent. The type of agent it is the opposite of what is happening to it. Right? All right. So in A, can zinc kick out hydrogen? Look at your reactivity series. Is zinc higher than hydrogen? Can zinc displace hydrogen? Yes or no? Zinc is higher than what? Right, so if you look at it, right, zinc is higher than hydrogen. So if those two were to come together, oh Lord, or this was supposed, I was supposed the answers were below these things. I'm not too sure why. Lord. All right, 1 second. The answers were supposed to be below those things, but it's not. All right. So you all want to complete that reaction. Let me do the first one for you. Since zinc can kick out hydrogen, the hydrogen will be on its own and the zinc will take the place of the hydrogen and the hydrogen gets kicked out on its own. Obviously, that's not balanced. I don't think that's a balanced equation there, right? I think you'll need what? A Cl2 here, because you'll need 2 chlorines to balance 1 zinc. Oh, and another way of doing this, you'll realize this is what? A metal, and HCl is what? An acid. A metal plus an acid is supposed to give you what? A salt and what? Hydrogen. So that's another way of looking at it. But it will only give you a salt and hydrogen if that particular metal is higher than H in the reactivity series. For example, if this was gold, gold plus this will give you nothing because gold is lower than hydrogen in the reactivity series. What about this one? This is a metal, and you notice this is water. Metal plus water will give you what? A metal hydroxide plus hydrogen. So for this one, you will get what? Sodium hydroxide and hydrogen. Well, I don't think it's balanced, but you all get the concept, right? What about C? C is a trick question. This is magnesium plus what? H2O, but it have a G. This means this is steam. Look back in your notes. A metal plus steam just give you what? A metal plus steam will give you what? When it's water, you just get metal hydroxide. But when it's steam, what do you get? Right, Alia, correct. You get something slightly different. You just get the metal oxide, not hydroxide, plus what? Hydrogen. But once again, I know that's not balanced, right? I don't think that's balanced. Actually, yeah, it is balanced. This one is balanced. And aluminum plus, this one is easy. Aluminum plus this. That's oxygen. A metal plus oxygen will give you what? You're supposed to get a metal oxide. So you'll get what? Al2O3. This is essentially aluminum or bauxite. Right? I don't think anybody want to balance this one for me. What number needs to go in front here? For this to be balanced. A 2 end? Yeah. Yeah, so 2Al2O3. All right. All right, guys. So that's pretty much the end of class. And next week is just strictly past paper questions on metals. I have a whole set prepared for you guys. All right. So I know you all seem very tired. So I will see you all next week. I'll see some of you all for physics on Sunday.